Okay, chapter 14. This is probably the easiest chapter of the whole book. I think probably what happened is the author was paid by how many chapters he wrote. So he added this chapter just so that he'd make some extra money. Because really, everything that you studied before in DC, resistive circuits, is exactly the same in this chapter for AC, resistive circuits. The key word here is resistive. Resistive. So as long as a circuit is purely resistive, all of this holds true. If we start adding some other properties, then what I speak of is no longer true. And we're going to get to that next chapter, in chapter 15. So with that being said, let's take a look at chapter 14. This should be pretty easy. After completing this chapter, you're going to be able to describe the phase relationship between current and voltage in a resistive circuit. Apply Ohm's law to an AC resistive circuit and solve for unknown quantities in series AC resistive circuits, parallel AC resistive circuits, and also solve for power in AC resistive circuits. Now, basic AC resistive circuit consists of an AC source, right? Conductors that connect the source to the load. And the key here is that the load is purely resistive. Now, when I'm beating this to death, what am I talking around? What do we make sure that the circuit has nothing of inside it? No phase shift. No, what components cause phase shift? No inductors or capacitors. So as long as there's only components in there that have resistive properties, we're good to go. As soon as there's a capacitor in the circuit, all bets are off. As soon as there's an inductor inside the circuit, all bets are off. But if it's an AC circuit that's made up of nothing more than purely resistive loads, we're good to go. Now what we see here, and we got to be careful about this because on the oscilloscope, what is it that we look at? On our horizontal axis is time, and on our vertical axis is amplitude, voltage. So what we're looking at here is a correlation between voltage and current. Can I see current on the oscilloscope? No. Can I see the effective current on the oscilloscope? Yes. So if you think you're going to call the oscilloscope up and say, well, look at this is current and this is voltage, you can't. All the oscilloscope will display for us is voltage over time. So we can't see this display on the oscilloscope. But we can look at this as an XY plot to show the relationship that voltage and current have. Now what I'm looking at here is pure Ohm's law. When voltage increases, what does current do? Increases. When voltage decreases, what does current do? Decreases. When voltage increases in the opposite direction, what does current do? Okay? And as a matter of fact, degree for degree, they keep up with each other. So when voltage is at 90 degrees, current's at 90 degrees. When voltage is at 180, current's at 180. When voltage is at 270, current's at 270. Make sense? Get my drift? So we say that these are in phase with each other. Now an AC source could either be an AC generator, we talked about that last week, where we have a rotating shaft cutting a magnetic field that we're generating AC, or it could also be a circuit that generates AC. Remember how we said AC, we have these different generators, function generator. There's circuits that could actually generate these waveforms for us. Typically, power is created by a generator. Signals are created by some type of a circuit. Now the load in an AC resistive circuit could be a resistor, a heater, a lamp, any similar device, as long as the only property that we're taking into consideration is resistance, period. When resistance is the only property that we're dealing with in an AC circuit. We're going to have voltage and current are going to be considered in phase with each other. Meaning at 0 degrees they're in phase, at 90 they're the same, at 180 they're the same, 270, 360. If it could pass that litmus test, we say that these voltage and current are in phase with each other. One of the things that I'm going to want you to do when you're dealing with these types of circuits, AC resistive circuits, are use the effective values. The effective values. This is the amount of AC voltage that produces the same degree of heat as a DC voltage of the same value. Remember this? When I apply 13 volts to this, it's going to be this bright and this hot. When I apply 13 volts AC RMS to it, it's going to be this bright and this hot, the exact same. This is an ideal example of an a resistive load. It'll behave the same in DC and AC effective applied to it. Exactly the same. So it can be considered the DC equivalent value. When we use that DC equivalent value, Ohm's law can be used in the circuit. Straightforward. E equals I times R, just like what you've been doing, with no modification. Series AC circuit, the most important thing about a series AC circuit, current is constant. Current depends on the applied voltage. Current is always in phase with the voltage. At any point, the current has the same value as the voltage. At 100%, current's at 100%. At 0%, current's at 0%. In phase. Parallel AC circuit, just like a DC circuit, the most important thing to remember is in parallel, voltage remains constant across a parallel network. Another term for a parallel circuit is a current divider. So total current divides among each branch. The total current is in phase with the applied voltage. The individual currents are in phase with the applied voltage, because it's purely resistive. All current and voltage values are the effective values. If they're not, what do you do? If I give you a problem like this and I start giving you values, what do you need to do? Convert. Convert to the effective. Always convert to the effective unless you're told otherwise. If you're in a tech manual and it tells you to measure, look for 17.4 volts peak, then look for 17.4 volts peak. But if not, always assume you're going to have to convert to the effective value. Now let me go back a step to last chapter. This isn't something I really shared with you at the time, but it's very important. With AC test instruments, why do we use an oscilloscope? See what's going on in the circuit. That's a good answer, because I did say it's for those of us that like to watch, if that's your thing.
So you can get a visual aspect of what the wave or the waveform is.
Yep. Yep, that's one reason. What's another reason? Why don't we just use our digital multimeters? It doesn't show the waveform. What happens if seeing the waveform isn't important to you?
You need to know what frequency is.
What's that?
You need to know what frequency is.
Maybe you don't care about the frequency. Can I use an AC digital multimeter for an AC signal to give me the voltage accurately? Bzzz. Wrong. That's why we have oscilloscopes. Basically, the digital multimeter for measuring AC is used for measuring AC power. AC power. What flavors does AC power come in? Remember this? This is review. Europe, what's the flavor? 50 hertz. North America, what's the flavor? Okay. SeaTac Airport, a 757 I just took off, what's the flavor? 400 hertz. Beyond that, A digital multimeter set for AC, pretty much worthless. Not worthless, you could accurately measure probably up to about 1,000 hertz. After 1,000 hertz, the numbers you get are garbage. So if I give you a lab that says you need to have a signal at 20 kilohertz and you need to measure 12 volts peak, do not get a DMM and try to measure it. If I tell you need 7.5 volts RMS, do not try to use a digital multimeter. Because above 1,000 hertz, the data just goes out to lunch. It's not designed to measure that repetition. It's designed to measure AC power. That is the #1 reason we really use the oscilloscope. Because the oscilloscope, you're looking at time versus amplitude, doesn't lie to us. That's one of the reasons that we taught you the math from last week. If you could see that peak value on your scope, you could calculate out that RMS value. You calculate out that RMS value, that's the real deal. So the fun experiment for you to do would be in the lab, do something at 60 hertz with the function generator, do 50 hertz, measure on your DMM AC, and then measure it on your oscilloscope face. Do 60 hertz, measure it on your DMM, measure it on your oscilloscope. Go up to 400 hertz, go to 500 hertz, go to 1,000 hertz. Go to 2,000, go to 5,000, go to 10,000. And what you're going to see is that accuracy is just going to, you're looking at the oscilloscope at the effective, the peak value, and you know effective is 70.7% of that. And your DMM is saying that you're way out to lunch. That's why we use the oscilloscope. Because above 1,000 hertz, most of them drop off. Some faster than others. That's actually the fun thing. What do you got there, Mr. Carter? What type of a METAR? Is that digital? So the fun thing to do would be to do a comparative analysis of that meter, one of our fluke meters, and an oscilloscope. And then just start gradually plotting it out and seeing and you'll probably be surprised that analog meter might give you the best above 1,000 hertz. Excuse me, but we don't use them above that. We don't use digital multimeters or analog meters for looking at signals. You have to stick it on a scope. Make sense?
You said the power is measured mostly using a device.
Power, for measuring power, electrical power, and electrical energy for consumption is typically, we use a DMM for that, a handheld meter. If you work for Seattle City Light, you really don't need to be climbing a power pole with an oscilloscope, okay? Because that meter is good enough to give you. If you're an industrial electrician, that meter is good enough. If you're a residential electrician, that's good enough. If you're going to play around in that lab, all of a sudden that meter now is really limited. Unless you're looking at the incoming power, if you're looking at a signal, you got to look at that signal on the oscilloscope. Make sense?
On fishing boats and workboats, I've seen they've got start up the gen sets and whatnot, and then they're phasing.
They're synchronizing with shore power? Yeah. Yeah, you want to be able to synchronize your generator with shore power so you can transition easy from shore power to internal power, and that's kind of critical the way boats are. In aviation, it's not that critical. You plug into a ground unit, and then the lights all go off, and ding, and then you're on the ground connection. But for a ship like that, it's got a big freaking generator. You want to make sure that you synchronize everything, and they actually have small meters that allow them to synchronize the phases, so that when you switch over, you synchronize and everything's still in phase. Because you could destroy motors and stuff by giving them a goofy phase relationship. So that's why you do that. In a parallel circuit, this is actually what we would be looking at. We couldn't see this though, because what do you see on the oscilloscope? If I put an oscilloscope across this right here, what am I going to see? I'm going to see voltage, right? I'm going to see the same voltage everywhere across this. Okay? But in actuality, what's taking place inside this circuit, let me go back a slide again. I've got current flowing through this resistor. I've got current flowing through this resistor. This current plus this current equals total current. So here's my current through R1. Here's my current through R2. Here's my total current. This plus this equals this. Make sense? Power in AC circuits is dissipated in the same way as in a DC circuit. It's measured in watts. Watts is what it's measured in. That's not a question, it's a statement. Okay, watts. It's equal to the current, literally, it's equal to the current times the voltage in a circuit. Voltage times current gives us power. P is equal to I times V, or E. Literally. What? What's up with this? This is odd, right? Okay, voltage times current. Voltage times current equals power. That makes sense, right? This times this equals this. Voltage times current. Well, I like your style. I like your, yeah, it's dissipated as heat, but literally, isn't voltage times current equal to power? So how come power isn't going to be? I like the fact that you say there's no such thing as negative power, but shouldn't this blue line be drawn down here? Do you believe that? Two negatives multiplied times each other creates a positive? I used to hear that and I never believed that. So let's see. I got negative $200 in my checking account and I go out and buy 2 plasma screen TVs and I'm going to have a plus balance in my checking account. It never made sense to me. But you know what? It is the truth. A negative times a negative equals a positive. And for those of you that are non-believers, here's living proof. A negative voltage times a negative current equals positive for power. And the reason is, as Mark said, there's no such thing as negative power. This would suck. You turn on your audio amplifier and furniture starts getting sucked into your speakers and, no, turn it down. You're going to get sucked in or something. It doesn't work that way. This is dissipative energy. So it's always going to be that heat energy that's given off. So there's no such thing as negative power. No such thing as negative power. Make sense? So for those of you that have swallowed the algebraic pill on that, a negative times a negative equals a positive, here's living proof. This is actually the first time in my life that I saw living proof. Other than that, I never really believed it. Never made sense to me. In an AC circuit, the average power is the power consumed. We multiply the effective voltage value by the effective current value. So it's that effective value, that RMS value. Sometimes you see the audio manufacturers playing around with that. 1,000 watts peak. Well, since your speaker is basically a resistive load, it's really going to be only the effective value that gets out, but it allows them to put, 14.7 gigawatts on the box or whatever for a marketing ploy. In summary, a basic AC resistive circuit consists of a voltage source, conductors, a resistive load. Voltage and current will be in phase with each other. The effective value of the AC circuits is what you're always going to want to work with, which is 70.7% of peak. So if you measure peak value on the oscilloscope, multiply that times 0.707, and that's going to give you the effective value. And unless it's specified otherwise, always convert to that. If I give you a peak value, say, why the heck is Joe giving me a peak value? Convert it to RMS. If I give you a peak-to-peak value, convert it. If you look on a radar manual, a tech manual, you're working on a radar and it gives you a peak value for something, assume they want you to know the peak value. Some stuff that is important, that you achieve a certain peak voltage. That will be specified in the manual. If the manual just says 14.2 volts AC, what do you assume? RMS. So if it's not labeled peak or peak to peak or anything else, assume RMS. Any questions?
On a generator, when you look at a generator,
Good question. Good question. If you've got a generator out there that says 5,000 volts peak, or typically, I think mine at home is 65, it's 5,000, it's a 5 kW generator, 5,000 watt generator, and it's a 6.5 kW peak. What that means is for a brief period of time that the manufacturer knows, it could actually, you know, it could sit there all day long and put out 5,000 watts, but for a brief moment in time, it could peak out. Like as a compressor on a refrigerator starting, it may try to consume up to that 1,500 watts more and then come back down. So the key on that is when they say peak, for how long can it operate at that peak value? For 2 seconds, 5 seconds, 10 seconds, 30 seconds, you know, and for some applications, it could be critical. You know, you could end up with, you know, basically popping a breaker or something, or overloading the generator if, you know, you hold it up there for too long a period of time. But that's what they mean by that peak output. Very good question. Very good question.
You'd also need to know the peak of that application too when it starts up, right? How long it holds that peak. Like if you got a vacuum cleaner and it starts up.
Right, right. And then normally, like I say, it's measured in a brief in seconds, you know, to see what loads. But the big thing at home, like with me, would be if my compressor was getting tired and it's trying to start and it's holding that up there really long, then pow, could pop that main breaker and shut the whole operation down. And I mean, yeah, that was a very valid concern when I put in a generator in my home, you know, to make sure I didn't exceed that and I left a big enough margin. But that is my generator at 6,500 peak, 5,000 continual operation. And it's always good. Whenever they give you anything like that, I always like throttle in the back a little bit, you know. Supposedly could run at 5 kW all day long. You know, let's underrate it. Let's run it at 4,500 all day long, you know, and I'll feel a little bit better not right up at its max. Because you are, if you're right at the max. And, you know, engineers have derated systems like that too. When they give you those specs, they assume worst case scenario, and you know, they always build in a margin of error so that they're exempt from prosecution.
Weight restrictions too.
Yeah.
You got something that has 1,000-pound weight restriction, probably put 2 on there.
Absolutely, absolutely. My incident that I was sharing with some of you last week for me, basically that the airplane we landed, it was 4,000 pounds overweight. From what Boeing said, it was okay, but if they say it's 4,000 pounds overweight, then it's probably good 20,000 pounds overweight, you know, to get the job done before things start breaking. So, good question. Any other questions, comments, concerns, trials, tribulations, grief, anguish, sorrow? All right, let's go ahead and take another brief 10-minute break. When I say brief, I mean brief, because then when we come back, we do have a bit of a challenge here, Chapter 15, capacitive AC circuits, game changer.